Hi everyone. So in this video, I want to give you an overview of the Chapter 5 assessment project and how that's going to work. What I'm going to be doing is it's going to be assigned to you on day 2. You will also have day 3 to work on it. Your deadline for submitting this will be at 9 a.m. at the beginning of day 4. Now, one thing I'm going to do at the day 2 is when it's introduced to you. You have all of day 3 to work on it. I'm going to have a Zoom session at the beginning of the hour on day 3 that you're more than welcome to join. You're not required to. You can Zoom in to the session at the beginning of the hour for about 10 or 15 minutes, and you can ask any questions that you have. You also are more than welcome to email me any questions you have on this project to help get some clarity. So the goal of this project is you want to draw a polygon that has at least 6 sides, and it has to be enclosed. It could be concave, it could be convex. Only thing it can't be is a regular polygon. So for example, a 6-sided regular polygon is a nice, perfectly looking hexagon. That's the one shape you can't do. But what you're going to do is the first thing here is, let's walk through it, is you're going to draw or find an image using only straight lines, a minimum of 6 sides, and it's enclosed. You need to label all of the interior angles to the nearest integer. You're going to measure all the exterior side lengths using centimeters. Then you're going to section off that polygon with non-overlapping triangles on the inside. So you're going to get 4 different triangles. You are then going to use your mathematics to get the measurements of those inside lines that you drew and all of the angles that you kind of cut. So if you had a full angle and you cut it into different sectors, you have to use algebra to find that. You're going to use SOHCAHTOA, law of sines, and law of cosines, your knowledge of geometry and angles, meaning if you take a 90-degree angle and you cut it into 2 parts, you could maybe use SOHCAHTOA to find one of the angles, and you could back into the other doing 90 minus that. This criteria here does state, though, you can't use a ruler or protractor to measure those interior angles and lines that you create. So I will talk more about that in my example. You're then, once you have all the side lengths and angles that you need, you're going to go ahead and compute the triangle formula and get the area of those 4 triangles. So you can use our new triangle formula, or you could use the standard right triangle formula. You are going to be required to use this one a minimum amount of times, though. Once you have the triangles, add them up and get the total area of the shape. I'm going to actually grade your project looking to see how easy I can follow it and how well that you use these different tools along with all of the work that you show. What you're going to ultimately upload is the image that you drew or you found and all the supporting math. So let's talk about the requirements in which you're going to be graded on. You must use at least law of sines and law of cosines each at least 2 times. That's not going to be hard to do. You are allowed to use the area formula of 1/2 base times height, but you must use the new one, 1/2 AB sine of C, at least 3 times. It's very easy to use this. 1/2 AB sine of C can always be used in exception to 1/2 base times height. Your drawing must have at least 6 sides. You don't need to have more. This does take some time to do, so I would recommend just doing 6 sides. The only shape you can't do is a regular hexagon. That means all sides and all angles are congruent. It's kind of the standard shape that pops into your head is the one you cannot use. And you must show all of your supporting math on how to compute your interior line lengths, breaking down adjacent angles, and how you got your triangle area computations. I would prefer if you could use no lined paper like typing paper. If you don't have it, notebook paper is fine. If you don't have a ruler to measure side lengths in centimeters, I'll try to post a tool in Schoology. You could probably Google also like a centimeter ruler, and you could get something to eyeball it, and you could be fairly accurate. For angles of the interior angle measurements, you can eyeball the angle measurements. I will try to find a protractor to put online too. You could also try to do that if you want, but you can eyeball it to be fine. How will you be graded? First thing is your ability to meet these 4 requirements stated above. Second is the accuracy of your initial measurements. Are your line lengths and your angles reasonable? If they are, fine, easy to meet that one. 3, the accuracy and the appropriateness of the math that you used. Are you using SOHCAHTOA on an obtuse triangle? If you are, that's wrong. You can't do it. SOHCAHTOA can only be used on right triangles. Does your math look fair and adequate? And then the last, how well organized is it? This doesn't have to be an art project, but can I tell where you're finding the area for a particular triangle? Is it easy for me to follow your math on that? So let me go ahead and give you an example of what I might do for this and how I would kind of think through it. So let's say this is the hexagon that I chose with my 6 sides. I'm going to get out my ruler and measure to the nearest centimeter for all 6 side lengths. And I have these measurements that I found. The next thing I need to do is measure the sum of all the interior angles. So remember from Geometry Exo, there was a formula for sum of interior angles. It was n minus 2 times 180 for a polygon. So in this case, we have a 6-sided object, so it's 4 times 180, which means the sum of the interior angles you come up with have to be 720 degrees. Now, you can estimate this. There's going to be a few that are pretty easy to do. Our bottom ones look like they're about 90 degrees, so that is at 180 so far. The other two that pop out here, it looks like maybe this angle and this angle might be congruent. To estimate that, I'm just going to kind of eyeball and notice that it looks like that's about 90 degrees there with this little bit more. So I would say that's probably about 120 degrees for that measurement. And then this looks congruent, so I'm going to say 120 for that. The last set here, these two here look like they are fairly congruent to each other. But what I do know is if I already have 4 of the angles are a 2 at 120 and 2 at 90, if you subtract that amount from 720, you are left with 300 degrees. So if 300 has to be equally split, we know that these last two would have to be about 150 each. So I can label that accordingly. Now, that is step 1, is just getting that set up. Step 2 says come on in and sector off the interior using diagonals to get your triangles. So I'm going to start right here because there's lots of ways to go. Maybe that right here is my first triangle. So I would have kind of this obtuse triangle might be the first one. I have a couple different options. If I wanted to, I could come on in here now. I could draw down here if I wanted to get another triangle. I actually don't want to do that. I feel like I want to go from here. So I'm going to do this as my next triangle. Okay. And then clearly I can come down to the bottom over here and get the other triangle. So now you're going to have the 4 triangles. By the way, folks, that's where this formula comes from. N minus 2 means there's 4 triangles that can be made in the sum of the interior, so that's why that happens. What you can't do when I talk about overlapping diagonals, for example, is if I were to come on in, let me just show you up here and go from like crossover. So when you see if I do that, what happens is this overlaps. So that's overlapping diagonals is not sufficient. So get rid of that. We don't want to have that option there. And we are ready to go ahead and start looking at how to compute the areas. I recommend trying to find the ones that look the easiest first, and then label the triangles. So maybe I'm going to say this is triangle 1, maybe this is 2, 3, and 4 for my triangles. Or if you wanted to, you could label your vertices like A, B, C, D, E, and so forth, and you could call this triangle ABC. So however you want to do that. Now, I'm going to show you how I would go ahead and start breaking down finding the 4 triangle areas. Keep in mind you have to use the 1/2 AB sine of C 3 times, so I can only use 1/2 base times height once, if applicable. Keep in mind that only works with right triangles. The way I have this drawn, there really is only one defined right triangle. It's this guy right here. Triangle 2 looks like it could be a right triangle, but here's where you have to be careful. On this triangle, all I know is this angle is 180. I am not guaranteed that this is 90. Even though I'm probably right, I am going to have to use some algebra to back into that angle. That's where this project takes some time. Okay, well, I'm going to get started, and I'm going to do that first one that looks the easiest to me. I'm going for triangle 1 here, and I'm going to try to find that area. And fortunately, this one's pretty easy. Triangle 1, I'm just going to maybe identify it this way, and I can jump right into the areas 1/2 base times height. It is a right triangle, so it's allowed to be used. So I'm just going to do 1/2. The 9 times the 6, which is going to get me 27. So I already have 1 triangle down, 3 to go. Now, let's look at triangle 2. This one is a little more involved. It's actually going to take more work than you think. So if I look at triangle 2, again, I cannot assume it's a right triangle because this is not defined as a right angle yet. I am going to have to use 1/2 AB sine of C, so maybe I just kind of write that down first. You don't have to do it this way, but this is what I'm looking for. I need 2 side lengths in the angle created by those 2 sides. What I might want to do is, as I look at this, here's what I see. I see I already have side length 6, so I'm going to go ahead and use that side length. Why don't I use this corresponding side length 2 and then find this angle? So that might be a nice way to go about doing that. To find it, though, I'm going to have to find, let's call this side length x. To find that side length x, I could use Pythagorean's theorem because it comes from triangle 1, which is a right triangle. So let's do that. X squared equals 6 squared plus 9 squared. To solve that, I'm just going to take the square root of that, and I'm going to get that x as approximately, that is 10.8. So I'm going to go ahead and actually add that to my picture so I can kind of keep track of it this way, if that is 10.8. So I do have side length A and side length B. I just need to get angle C. How can I go about getting angle C? Well, what I probably could do is back into, if I take a look at this, finding this angle here on the first triangle. If I can find this angle on the first triangle, I'll call that angle A. Then to find if I call this one angle B, I know that full angle is 90 degrees. So why don't I take the full 90 degrees minus angle A, and then I will have angle B, and I can do this. So to find angle A, it looks like I'm going to have to use some type of SOHCAHTOA. I could do tan. So I'm going to do the tan of A is equal to 6/9. Okay. How do I find the measure of that angle? I do inverse tan. So inverse tan of 6/9, and that is going to give me approximately 33.7 degrees. So I know that this is 33.7. Can I back into angle B? Absolutely, that's easy. Show the work though, folks. 90 minus the 33.7 is going to get me the 56.3 degrees. So that's going to be 56.3 degrees, and I'm going to add that to my picture. And I'm ready to go ahead and actually compute this area formula now. All I need to do is go on in, and I'm going to just tuck it down here real quick. Area equals 1/2. I have 6 times 10.8 times the sine of 56.3 degrees. And what you get for this area is 26.955, which rounds to about 27. So the area of triangle 2 is approximately 27 degrees, which makes sense because even visually, we could tell that this area of this triangle is going to be the same as this because it's just a standard quadrilateral cut into 2 congruent pieces. But you have to prove it. Triangle 1 was easy to prove with 1/2 base times height. Triangle 2, I had to back into all of this work to get it. But the nice thing is I'm 2 triangles in and only 2 more to go. So let's talk through how would we look at the area for triangle 3 here. Well, it's clearly not a right triangle, so I have to use 1/2 AB sine of C, plus I have to use it 3 times, so I'm going to have to do it again here. But I need 2 side lengths and an angle. What I could do is I'm looking at triangle 3 and I noticed this. They have given me one of the side lengths, so I'm going to use side length 4. And then I'm going to piggyback and use this side length here and then come up with this angle. So for coming up with that one, I already have the 4. I need to get the other side length in the sine of the angle. So how do I do that? Again, it's going to take me a little bit of work. I'm going to have to back into, it looks like, if I could get this angle here, what I do know is I could fill in this angle. So this is a right triangle in triangle 1. So that means this guy here would be 180 minus 90 minus the 33.7. This is 56.3 degrees. So if this is 56.3, what if I find this angle, and then I could subtract these 2 small guys from the complete 120, and I'd have the third angle nicely. I can use the current information in triangle 2 to find this other missing side length. If I take a look at that, maybe I will try to find this side length first. So this side length, what I could do, I need to find that. That's side x. Well, x matches up with this angle, and then why don't I use these two side lengths and do law of cosines? The law of cosines will get me that missing side length. So for triangle 3, I'm going to start by doing law of cosines, which is x squared equals 6 squared plus 10.8 squared minus 2 times those side lengths times the cosine of the angle is 56.3 degrees. Now to solve this, just come on in and take the square root of that, and what you're going to get is it comes out to be approximately the number 9. So this side length is about 9 units long. Fine, I have it. So 4 times 9, now let's find that angle. So to find that angle, what I have to do is back into this angle here, which I could easily do now by using a law of sines method. So if you've labeled everything along the way, you're going to see we have a nice law of sines relationship. If I have to find this angle, here's its side partner. Well, I have this angle and I just found its side partner, so let's write this particular formula. Is going to be, I'm just going to call it the sine of angle x over 6 equals the sine of 56.3 over 9. If we solve this one, we're going to do inverse sine of 6 times the sine of 56.3 over 9. And when you do that, you're going to get that this comes back to be about 33.7 degrees. So again, you may have thought, well, can I just back into that? Because I think this is 90. We don't know it's 90. We haven't proven it. So you have to do the math on that one. But the great thing is we have the angle, so let's pop that in there. And if you put this in here and you solve it, what you're going to get is that it actually comes back to an area of about 9 centimeters squared, which gives us triangle 3. Okay, let's keep going and wrap up with triangle 4 now. Now, as I look at triangle 4, my brain first says, okay, I need to find the area of here, 1/2 AB sine of C. Maybe I need to back in and find some other missing side lengths or angles. But wait a second, maybe I should look and see this. I already have a relationship set up for it. This thing is ready to go. I have 2 side lengths and the corresponding angle already. So this one is not going to be tough. This is a nice, easy one of taking the two side lengths I have, the angle that those 2 side lengths make, take the sine of it, and compute the area that way. And this comes back to being about 3 squared centimeters. So I've computed all the 4 areas, add them up, and you have your final answer. Just make sure to organize this nicely so it's easy to follow. I know it wasn't the easiest to follow on my video here, but hopefully that gives you an idea of where to approach it. Again, good luck. Let me know if you have any questions. You can send me an email or you can join our Zoom session. And those Zoom sessions are going to be for 4th hour, your day 3 is on Friday and your class starts at 10:30. So Zoom in at 10:30 if you want to join the session and ask any questions you have. Day 3 for 3rd and 7th hour, you're that next Monday. 3rd hour, you're at 10:30. 7th hour, you're at 1:45. Again, just click on the Zoom assignment in the day 3 folder, and that will give you the information on the code to use to join that session. Or email me. My email again, if you need that, is just landon@277apps.org. Please make sure to email me. My sister-in-law also works at the school. She is Landon D. That is not me. I will not get it if you do that email. Good luck in then getting this posted. The deadline is going to be at 9 a.m. on your day 4. So for the 4th hour, that is going to be Tuesday at 9 a.m. For 3rd and 7th, that is going to be that following Wednesday at 9 a.m. And this will be wrapping up of Chapter 5, and then we will move on to Chapter 7 after this. Have a great day.